All right, so approximately page 182, you can see some of the, let's say, orbital diagrams that we have been going over, and hopefully we can take this content and illustrate what we mean by valence electrons. One of the things that we had learned last year is what is, and it's on one of those 2 pages, the simplest, let's say, molecule or bond that can be formed from the periodic table is what?
Hydrogen.
Right. Because what happens is when you do that orbital notation, okay, we know
It's just HH.
you have 2 hydrogen atoms, each like this. Now, what you might be asking is, well, what happens when both of them are pointed up? Well, I would say, good question. So, what you see there on page 182 is that when these are spinning, okay, they still would repel one another, and the proton inside that atom would still want to grab a hold of that electron. And notice that when we do these are in neutral states, but when we combine them, you would have to have that moving in the opposite direction. Okay? One of the things that maybe could be a low down dirty trick is maybe if a question was to state what happens if you did the 4 quantum numbers for these here. Well, is there any of them that would or will overlap? Well, what is N? What is L?
0.
What is M?
1. Scooting. 0.
What is S?
1.
Okay? Then, should you do this electron, then we've got what? N is,
1.
L is,
0, M is 0. How can you change it though?
You don't.
well, when we do, with every atom that we've done, it was just illustrating what the orbital diagram would look like. Now we're actually showing that a bond is actually going to form. Okay? And the only way you can do that is you can't have this pointing up because they're moving in the same direction. So in a dashed line on page 182, notice that they have one arrow pointing up and one arrow pointing down. And on the left, you see it says hydrogen atoms, and then it has an arrow to the right, and then what does it say to the bottom of that rectangle? It's actually a hydrogen molecule that these then overlap, which then gives you this stable configuration of the most stable molecule on the table, because there's only just one electron.
Yeah.
So that same type of concept you could apply for what they're showing as far as fluorine, okay? So moving forward, if you were to do one fluorine atom, we know you would do 1s, 2s, and then 2p, okay? So how many electrons are in fluorine, a neutral atom of fluorine?
9.
Okay? So then how many arrows are we going to have?
9.
Okay? So that's pretty straightforward. This one's pretty straightforward. So now we're up to 4, so we have 5 left. So one of the things you could do, I would suggest, until you get a really good understanding, you can go ahead and do this. Okay? You can start pairing them up right away, but you'd really have to be careful with what it is that you're doing. So now, if we had another fluorine atom, we could say the same thing, 1s, 2s, and then 2p. Okay? So what that again is illustrating is another way of looking at this is just the valence electrons as well. So when these overlap, what happens when when this orbital combines with this one? Just the same thing would happen with here. So if we put this red arrow up there, now that has a filled outer energy level. And then you could say the same thing for this one. Oops. There we go. And we can also illustrate that because what column is fluorine in? Okay, so then what happens is we'll go ahead and illustrate. We've got fluorine. And why would you not say 9?
Because that's how many electrons it has, not what column it is.
That's how many electrons it has. This is in an inner energy level. Remember, valence electrons are those that are in the outer energy level. Okay? So we could look at all the black arrows we have, and that is what? How many of those exist? That are valence electrons now.
7.
Okay? And for 2 reasons we know that. Because it's in the 7th column. Okay? We have 5 black arrows there, and then 2 black arrows here. And how do we denote valence electrons? Yeah. I mean, as far as making a diagram, sorry.
Dots.
Or X's, E's, slashes, triangles, any one of those. So to me, I've always just liked doing something other than dots. Okay? So those 7 X's represent those 7 arrows. Then, if we were to do this, do the same thing with another fluorine atom, but we're not, and we can use X's again. Okay? So then the same type of idea that you see on what, 137 maybe? 183, sorry. Then once we combine those, just like clicking and dragging all this up here, and then that shows us our bond now. Because they are sharing what you see in between here. And that's just a different way of what they're illustrating on page 183. Okay? So in other words, on page 182, the octet rule. Unlike other atoms, the noble gas atoms exist independently in nature. They possess a minimum of energy existing on their own because of special stability in their electron configurations. The stability results in fact that, with the exception of helium and its 2 electrons in a completely filled outer shell, the noble gas atoms, outer s and p orbitals, are completely filled by a total of 8 electrons. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. Such a bond formation follows the octet rule. Chemical compounds tend to form so that each atom, by gaining, losing, or sharing electrons, has an octet of electrons in its highest occupied energy level. And that highest occupied energy level is where you find the valence electrons. And that's, in short, what this is trying to tell you. Let's examine the bonding in a fluorine molecule. Illustrates the octet rule. An independent fluorine atom has 7 electrons in its highest energy level. 2s2, 2p5. So that's what we have illustrated here. 2s2 and then 2p5. Like hydrogen atoms, fluorine atoms bond covalently with each other to form diatomic molecules. When two fluorine atoms bond, each atom shares one of its valence electrons with its partner. The shared electron pair effectively fills each atom's outermost energy level with an octet of electrons, as illustrated in figure 9a and 9b. Okay? And you can do that, and to me, it's more so of an ionic bond on that bottom one, but for real technical purposes, that's still a type of covalent bond. Okay, so figure 9a and 9b shows another example of the octet rule in which the chlorine atom in a molecule of hydrogen chloride achieves an outermost octet by sharing an electron pair with an atom of hydrogen. Okay, so in this case, I think we'll just do the same thing. We'll just keep it simple with fluorine. So why can we do fluorine and not use chlorine? Is there some similarities there between chlorine and fluorine?
They're
Both
both
end up
halogens.
Yeah.
When you say they're both halogens, that's right, which means you know where they're at on the table.
Seventh column.
Which means they're in the 7th column. The column number also
Does that
tells
have to do
you.
with chlorine's negative one charge? Or no?
Is that, say that again?
Does it have to do with chlorine's negative one charge?
Yeah, it does.
'Cause
Okay.
it's-
So now, if we wanted to illustrate this with what we just read, I'm going to go ahead and take this, and what color marker am I going to get? If you can see. Say that again?
No.
I could have swore you said green.
Yeah, green.
Oh. Does that look green?
Just a little bit.
Really?
Purple.
Yeah. I'd say it's more so purple. So then that's where that electron is. So here's our hydrogen atom. Then all of these red arrows then is our fluorine atom. There
How
we go.
come the hydrogen's up and the other one's down?
Well, you can flip-flop the two if you want. It just happens to be that since that one's down, I just said, well, that one's got to be up. That's how that would have to bond together. So to answer your question, you said, is that how it gets its charge? Well, when we look at this, we know that there's 9 protons in here. So 1s2, 2s2, and then 2p5. Okay? So we have 9 electrons and 9 protons. But what has happened then is we had this hydrogen atom. I don't know why I did that. That just had 1 electron in it. Okay? Then eventually what happens is here, oh darn it. That's right. It's just I want to be more accurate. Now I know what I'm doing wrong. That's still right. I picked the wrong color. That's still 9. That's still 2. That's still 2. That's still 5. Okay. Now we're on the right track here. And then this is still 1. That is still 1. So then what happens is this electron will move over to here. And I don't like it when these, when I go through that color, then it starts to trail. And then the red and the purple mix together. Now this is gone. The energy level is still there. The energy level is still there, but it's empty. Okay. So then, how many positive charges in the nucleus?
None.
One.
In the nucleus.
One.
Okay. How many negative charges are out here?
One.
Okay? So this has one proton, no electrons. So that is a charge of what? Okay?
Can it make methane if it has no electrons?
It has to. Or else because we know that this exists, and if it didn't, then we're in trouble. Then a lot of chemistry that we've learned and taught over the last 200 years would be incorrect. Not 200 years, I don't know if that's right, but just sounds good. Okay, how many positive charges are in the nucleus? How many negative charges are on the outside?
1.
I don't know.
7.
5.
-1.
5.
0. 0 positive charges.
There's 9 positive charges. How many negative charges are out here? How many negative charges are out here? How many negative charges? I heard it. 10. Okay? So if there is one more electron than proton, then this has a charge of negative. And again, that's where those numbers come from. Okay? And maybe you'd said that a long time. I said that a while ago.
I said that a while ago.
Okay? Things like that happen. So some of this is going to be a review. Okay? So the next page deals with electron dot notation. And I just want you to look at figure 10. And what do you notice there in figure 10? The left-hand column says number of valence electrons. Okay? So in the middle column says electron dot notation. So then, would you just be limited to sodium in figure 10 for the first horizontal line across? What? Yes, just an example. What else could you give?
It would be anything in that first.
In the first lithium,
Lithium.
potassium,
What else could you use besides not
hydrogen.
in that column? That's not in that column.
Helium.
Excuse me.
Not helium.
Dang it, it's carbon.
Not carbon.
Oxygen.
No. Okay, we're not quite communicating here.
It'd be like some,
Because you said everything in column 1, which means it has one valence electron, correct?
Oh, yeah.
So then, if it has one valence electron, what's it going to do with that lone?
Give it away.
It's going to give that away. The point being is that you would need to pick an element that has a +1 charge. So you're not just limited to the alkali metals. So it must be something that also forms a +1 charge. Silver does that. Copper does that. Gold can do that. Okay? So that's what we mean. You're just not totally limited to that. And there might be some more over here. Yes, we got silver's +1, gold +1, +3. Yes, that's right. Mercury +1, +2. Now we're probably about out. Okay. Other than copper. Copper could do that too, because it's +1 or +2.
They should make one called cadmium.
Now, one of the things that you might discuss, I don't know how far in depth you go if you take this course in college, but it's one of the things that we wanted to illustrate, and we could use, I think it makes the most sense since we said copper to go ahead and do that one. Okay? So what we see happening here is inside the nucleus of copper, atomic number 29. Okay? So, if we follow our slide rule, we know these numbers have to add up to 29. So it's 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, and then 3d. Okay? That's something I didn't do earlier either. But notice the reason we chose copper is because we said it can form this charge or it can form that charge. So I think it was a question on your problem quiz a while ago. What would be the most logical way for copper to form either a +1 or a +2 charge? +2 is pretty simple. You would take away these two, okay? And then what you would see happening is, yes, the energy level is still there,
He's got extra 2.
but then you add all these together, are you going to get 31 or 27? You're going to get 27 because you're short 2 electrons, okay? And if we wanted to just double check and make sure, that's 18, 18, or that's not 18, that's 12, and 9 gives you 21, 23, 25, 27. So that's got to be right. But how could it possibly form a +1 charge? Well, what happens is sometimes these elements can be just as stable if their outer energy level is half filled. So then we won't go too much beyond that because half of 2 is 1. That still has to be a logical way of looking at that, because your table, the one either that you have in front of you or that was given to you at the beginning of the year, or Bob over there, you look inside element 29's box and you would see +1 and +2, and that's why that does that.
You just know that.
Does what just know that?
There's no way to really find out how stable it'd be. Like people just.
There is, I suppose, without getting, well, I like to say, without getting into the weeds or going sideways too much. In other words, we'll just say you're on a golf cart. We're not in your vehicle. We're on a golf cart, and it's slippery roads, and should you go off the road, you just slide off. You don't roll anything or anything to that effect. That's what we mean by starting to go sideways. The question that you're kind of asking, this is something that you would probably need to be able to use, not memorize this, because this is just way too much to know.
Don't they use organic chemistry?
This year? No. This is still general chemistry as well. And what this is showing is different types of voltages that these atoms will form, and these are known and accepted values. And then, since it's in alphabetical order, what you would do is find the element Cu, and then notice that what we see happening is right there by my thumb. It can form those two different charges, and it does give a positive value. Some of these actually form negative charges, okay? And it just depends upon where they are on the periodic table, because these are some of their physical properties then as well. So does it just know that? This you're using upon what you're reacting with. We say, does it know that? No, it doesn't. It just depends who it wants to be paired with. And that's without trying to go sideways into the weeds and just trying to, oh my gosh, make this more difficult than what it has to be. We really don't want to do that. So if you remember when we were freshmen, we probably spent, it's just a guess on your part. We probably spent 3, 4, 5 days on this. Here, we're probably ready to go, looks like after 2 days. Okay? It probably was even more than those 5 days. But we just go at a faster rate because we're on the bus. Okay? So I think that's good enough for an introduction here. We will catch up to you next time.